Hello, everybody. We'll be getting started in just a minute here. Good afternoon, everyone. Thank you for joining the National Institute of Statistical Sciences and the Federal Committee on Statistical Methodology for the second installment of our AI in Federal Government webinar series. I'm Ed Strocko from the Bureau of Transportation Statistics, and I will be our moderator for this webinar. I'd like to give a special thanks to our sponsors, the American Statistical Association, NORC at University of Chicago, and RTI International. Their generous support is much appreciated. Today's webinar will cover text analysis, methods and use cases, and we have a great lineup of speakers. A few logistics for our webinar. We will have 90 minutes together this afternoon. Our 4 speakers will present for 15 minutes each, leaving us approximately 20 minutes for questions, answers, and discussion. If you have a question, please use the Q&A function to ask your question. We will look to tackle your questions after all of our presenters have spoken. To get us started, let me say a few words about each of our 4 speakers. Benjamin Rogers will discuss text analytics, background on large language models and their usage. Ben is a data scientist with the Division of Research and Methodology at the National Center for Health Statistics at CDC. He is experienced in integrating AI technology into public health initiatives, specializing in AI and machine learning. Ben has played a crucial role in assessing the utility and risk of conversational AI technologies like ChatGPT, demonstrating his commitment to responsible AI adoption at the CDC. He contributed to the training of the publicly released NCHS AI model, the semi-automated non-response detection for surveys. In 2022, Ben presented at the Federal Committee on Statistical Methodology on using natural language processing for survey response analysis. In 2023, he participated in APOR, showcasing collaborative NLP efforts in survey text analysis. Ben holds a Master of Science in Data Science from the University of Virginia. Ken Haase will discuss why meaning matters, grounding for text, data, and statistical products. Kenneth is a senior computer scientist at the Census Bureau and has a diverse academic background, spending a significant portion of his academic career at MIT. Beginning in mathematics and transforming and transitioning through to philosophy, he earned his master's and PhD degrees in computer science at the Artificial Intelligence Laboratory. As a professor at the MIT Media Laboratory, he focused on semantically rich metadata and case-based representations. Notably, he co-developed FramerD, an open-source object database designed for large pointer-intensive datasets. Professionally, Kenneth has held various roles, including software developer, designer of physical and virtual interfaces at Atari, researcher, research manager, professor, entrepreneur, and laboratory director. In 2001, he founded Being Meta, a company dedicated to creating technologies that enhance human access to information, leveraging his work at MIT. Brandon Kopp will discuss clustering Federal Register comments for efficient manual review. Brandon is a seasoned research psychologist with a rich career that commenced in 2010 at the Bureau of Labor Statistics. Within the BLS, Brandon serves as a survey research advisor within the Behavioral Science Research Center in the Office of Survey Methods Research. His primary focus revolves around labor economics, where he plays a vital role in designing questions for long-standing surveys administered by the BLS. Committed to enhancing the reliability of data across time, Brandon engages in basic research to improve various aspects of the survey process. This includes refining the user experience through website usability projects, where he collaborates with website users to identify potential enhancements. Several years into his tenure at BLS, Brandon enjoys a rewarding mix of independent and team-driven projects, showcasing his proficiency and passion for programming and data science in his diverse and successful professional journey. Tala Fakhouri will discuss using AI-based technology to increase operational efficiencies at the FDA. Tala is the Associate Director for Policy Analysis in the Office of Medical Policy Initiatives, Center for Drug Evaluation and Research at the Food and Drug Administration. Dr. Fakhouri manages a team tasked with developing, coordinating, and implementing medical policy with a focus on the use of artificial intelligence and machine learning in drug development. These efforts include overseeing an AI policy group, as well as engaging external stakeholders and advancing the development of regulatory science around the use of AI in drug development. Recently, she led the development and publication of a discussion paper titled Using Artificial Intelligence and Machine Learning in the Development of Drug and Biological Products. She also contributes to the development of medical policy related to real-world evidence and the use of digital health technologies for medical product development. In 2023, Tala was selected by the Office of Management and Budget to serve on the FCSM for her expertise in statistical method. Ben, we will turn to you to get us started. The floor is yours.
Amazing. Thank you so much, Ed, for that introduction. Go ahead and start sharing my screen. All right. So thank you, Ed. My name is Ben Rogers. As Ed mentioned, I work for NCHS as a data scientist. And important thing to note about me is that while I've only been doing research with large language models for the past 3 years, the modern large language model that is only roughly 6 years old. So I've been using them for roughly 50% of their existence. And that includes actually publishing a large language model, like Ed noted. Their model card for it is up on cdc.gov, and it's available on Hugging Face if Hugging Face is up today. But main reason why I am presenting here is I'm going to be giving an overview on the tech behind the next talks, something I'm very excited about, and I really hope to share some of my enthusiasm about large language models and their usage as a whole. So just as a little background, there's a lot of text on this slide. Don't need to worry about reading it, because we're just going to go to some fun parts here, which is actually visuals and be able to see it. So our first part here is the embedding. So an embedding is a high-dimensional representation of text. Essentially, when I say the word embedding, what I want you to think of, if you have no idea what that means, just think at the bottom there, we have that Excel row. And so we have the word the. That representation of that text, the large language model doesn't really see it and doesn't see, oh, the THE, I know the meaning. That could be in a bunch of different things, what that meaning is. All it sees is the 3 characters, a T, an H, and an E. And so to represent the actual meaning of the text, it'll create this long series of numbers and values. And that means that in hundreds and hundreds of columns, essentially, there's a value between 0 and 1 present. So when I say the word embedding, just think single row in an Excel spreadsheet with hundreds of columns, and each column has a value. And just think of that. Now that row can mean multiple things. It could mean a whole document. It could mean an individual word, anything in between. It doesn't even have to be text necessarily that it represents, but it's just a representation as an Excel row. And you may be saying to yourself, Ben, why does this necessarily matter? Well, if you've ever looked at the dictionary, even a simple word, a simple quote unquote word like the, has so many different definitions. And if you look here, there's at least 4. For this screenshot that I took, I believe for this first definition, there was 12 when I looked on Merriam-Webster, and there was 3 other definitions as a whole of the word the. There's so much meaning that for a large language model to properly grasp the context and the full concept of the word, it needs all those hundreds of values present in the embedding. And so next, we're going to talk about what actually is using that embedding or that representation. And also for more usage of embeddings and meaning as a whole, I'd like you to point out to stay tuned to listen to Kenneth's talk about meaning and Brandon's talk about clustering, because both of those will be talking about A, meaning, and B, embeddings as a whole. But a large language model, or an LLM, that's oftentimes what they're called, a little acronym, because everybody loves a good acronym. These are a class of language models that use deep learning algorithms and are trained on extremely large textual data sets. Think up to trillions of words now. It's massive, a large amount of data that's available on the internet. And most of these, like for example, your GPT-4, your ChatGPT, or your Google Gemini, for any of you Google Gemini users out there, what these are largely they're autoregressive large language models. And what that means is that it uses the word it predicts to help predict the next word. And so when you have your model, these large language models, they take in your text and they kind of operate kind of like Family Feud, the game show, where it's given this input as a sentence, and then, okay, it makes the most likely answer as the output, that most likely piece of text. So for example here, if you were to ask a large language model, okay, write me a story. Well, the model would see this as your text. It'd go and say, okay, write a story. What's the most likely word next for the output? Well, the is a pretty common word, you could say. And, we have to have something for it to be about. This is a pretty blank canvas, so let's just make it cat. The cat. Okay, so that's our starting point for our story here. Pretty decent. I mean, not great. There's not too much to it, but what else can we add? So now this autoregressive large language model is going to take in that text and it's going to add it to that input. So now the model has as its input, it's calculating all those embeddings, creating all those little Excel rows with all the hundreds of values. It's not actually an Excel sheet. It's just for the concept visually to help. It's going to look at write a story, the cat. And now it's predicting the next word following cat here. So what is the next word that it could be? Well, in that's pretty good, following the grammatical structure. Okay, that makes sense. We have a good grammatical structure sentence going here. And now towards the end, you could say, okay, now let's add all this text in, write a story, the cat and the, I think you all can see where this large language model is going. Output hat. We're starting with some Dr. Seuss here, the cat in the hat. So as you can tell, I'm pretty excited about this subject. But one thing I do want to share really that I'm really excited about in terms of the frontier is in context learning. And so context here means all the information that you give to a large language model. And so at the ends there, the context was, okay, write a story, the cat in the, that was the full context for these different large language models. And why this kind of matters is for your traditional learning for these large language models, you have your base model trained on these thousands, these millions of words. It can create that representation of text, those embeddings, and then it can use that to predict the next word out. But it's only trained on so many different tasks, and that doesn't always fit your needs as a user. And so how you can sometimes get those needs met is you can fine tune the model. So for example, here, this is a screenshot from the paper, Large Language Models Are Few Shots Learners by OpenAI. That's for the GPT-3 paper, for all of you out there who know. This example here is for a English to French translation task. So there's a ton of different tasks you can use with natural language. This is just one of them. And so what you can do is if you want to focus your large language model onto this task, have its embeddings be focused on the value created for your translation task, or have the model that output the probabilities of the words change to focus on translation. You can have the model actually update and learn how to translate. So how it does this, you give it dozens and dozens of examples. You just keep going, hundreds, if not thousands, so many different examples. And after every single one, you see that little text that says gradient update. That's just the model changing. So the model has slightly adjusted until by the end, you have a new model that's focused on this task here of translating from English to French. Now, what's really fascinating about modern large language models is you don't actually need to fine tune them anymore. They've been trained on so many different tasks for a lot of different situations. You don't need to train them because they are pretty good at zero shot performance. Zero shot here means no examples given. So all that context, for example, for a translation task, all we have to do is describe our task, translate from English to French. We give it our prompts, cheese, and then it can go. We can give that to our large language model. And a lot of the modern ones today would probably crush this task. It's pretty simple. All you have to do is give it some information. The model doesn't change in any way, shape, or form. And so this is called zero shot performance. There are no examples given. But what's so fascinating is if you just give the large language model a few examples, to add in to show how you can perform this task, the performance will increase, which is absolutely amazing. This is called few-shot learning, and it's so fascinating because there is no model change going on. The model is creating the same embeddings, how that process is being made, the exact same. The model itself is not changing in any way, shape, or form, but just by changing the text going in and giving it a little bit more information, you can increase your performance of the large language models, which is so cool. It's so amazing. And so just as kind of an overview for the amount of effort you can really see on the screen, on the right there, that's our fine-tuning process. And you can see how many thousands of examples. This is a time-intensive, a compute-intensive process. And then on the left here, this is our zero-shot and few-shot examples, where all you have to do is type in a few words, and you can have your AI be able to help you with whatever task you are, whether that's translation, few-shot classification, all of those different things it can help you with. And so kind of just as a summary overall, kind of some tips and tricks I picked up on over the past few years. You're going to want to fine tune a model when a task is expected to be common and repeatable, and you need consistent output from a large language model. Because it's based off of the probability of the next word, if it's very close, if the probabilities are very similar, that can change what output comes out. So if you want the same output every time for a piece of text going in, you're going to want to fine tune a model specifically for that output. You're going to want to use few-shot prompting and prompt engineering when you have roughly 50 high-quality data points or less available, and you can justify your output succinctly. You want it to be very, very succinct in that text, even less maybe than all the text on this slide here going in, because there's only so much space you can fit into the context window of your large language model. There's only so much information that can go in. And as always with these, you want high quality data over high quantity, quality over quantity every single time. If you only have 1,000 high quality data points for fine tuning, that's fantastic. You don't need to go to the 10,000 if it drops down to a lower quality. High quality is everything here. And overall, though, for effective usage with large language models, you're going to want to identify output of interest, including any reasoning or edge cases. You want, again, that high quality data, high quality, high quality, high quality. That's all that matters. And you're going to want to also identify what resources you have. If you don't have the compute to fine tune, then you're going to have to few-shot prompt. But luckily, as we see here on this slide, is that few-shot prompting actually can give a decent performance here. So I said earlier that these improves performance. This is some actual published research demonstrating this. This is from the Llama 1 model paper. For this task, this is a table showing performance and the trivia Q&A, which is a closed book question answering large language model benchmark. The three models here are no longer state-of-the-art, but they're still pretty big large language models in the research space. That's Gopher and Chinchilla by Google. Gopher published in 2021, Chinchilla published in 2022, and then Llama, which was published in 2023. And so as you can see here, for the top for a 0-shot, 1-shot, 5-shot, those are the number of examples in that prompt again that the model is given, and then performance. And a couple that I want to give a kind of a takeaway to show is that when you look at Chinchilla for a 70 billion parameter large language model, I know that's a crazy number of parameters. These models are massive. It has 70 billion parameters in a 0-shot setting. Compare that to Llama, which has a tenth the number of parameters. With just 5 examples, Llama 7B performs just as well, if not slightly better than Chinchilla. And so if you don't have access to GPT-4, but you have access to a smaller large language model, few-shot prompting can get you to a near performance of that GPT-4, or that large language model. And this is also true for large language models within the same family. So Chinchilla and Llama, they have different training data sets, the different ways of training. And when you look at within that same data set that has the same amount of training, the same training tasks, all those combined together, for example, here, Llama 33 billion versus Llama 65 billion, that 0-shot to 5-shot comparison still holds true. Llama 33B in a 5-shot setting outperforms 65B, or roughly the same. And so you don't necessarily need all that compute going into running these massive large language models. I mean, you perform pretty well with a smaller one. But I know, Ben, I've been talking about gophers and chinchillas and llamas. So the question is, at the end of the day, among all these racing large language models with animal names, who wins? And the answer at the end of the day is you. This image was created by DALL-E 3 for context for everyone, this is generative AI. And why are you the winner, Ben, of all this? It's because large language models can increase productivity. This is, I'm citing here a study in the Harvard Business School that was done in conjunction with the Boston Consulting Group. The Boston Consulting Group does have their own version of the study published, which is a little more hesitant, but a couple of key bullet points. Number one was that consultants on 18 tasks that were deemed within the AI frontier, for the consultants with GPT-4 plus some prompt engineering training, they completed 12.2% more tasks on average. They completed those tasks 25.1% faster. And then the big one, 40% of their tasks were completed with higher quality. So at the end of the day, if you never use a large language model for text analytics, that's totally fine. It can impact your life in so many other ways. And mostly it's this increase in productivity. If you want to hear more about that, pay attention to my colleague Tala's talk at the end. So thank you so much. Here's some citations for the things I've referenced here. This is my smiling face. Here's my email, brogers2@cdc.gov. Feel free to reach out to me if you have any questions or comments about large language models. But thank you so much.
Thank you, Ben. That was excellent. Really, what a great way to kick this off. Really enjoyed that. We're going to jump over to Brandon next. Brandon, floor is yours.
All right, thank you. And thanks everyone for coming. Today I'll talk about text clustering and how it can help aid in manual qualitative review of text responses to surveys and from text responses that are received as part of surveys or forms that we have in government. And I chose this topic because it's a relatively simple way to add value to a text review project. And the techniques that I'll talk about would make a good early project for you if you're looking at experimenting with natural language processing. Before I start, I want to mention that all of the data and all of the summary data that I'll share with you today are public, and I didn't have any special access to information as part of the project that I'll be talking about in this use case. I'll start with some background to better help you understand the use case, and then I'll get into some more technical aspects of things. For those of you that don't know, the Federal Register is a government publication where agencies provide notifications of significant events, of new regulations, executive orders, and so forth. And the Federal Register is also used to request public input on important issues. The Federal Register is a mandatory part of a lot of official government workflows, and there are dozens of notices that are posted every day. When Federal Register notices seek public input, regulations.gov is where the public are sent to in order to leave their comments. There are usually some predefined windows for these comment periods of like 30 or 60 days, for example. And in most Federal Register notices that are open for comment, you'll find a box that directly links to the regulations.gov page where you're supposed to submit your comment for that particular FR notice. Most notices receive few, if any, comments, but some capture public attention and receive a lot of comments. And announcements can come as short text that gets typed into a comment box on regulations.gov or as attachments, perhaps PDFs or Word documents. And some organizations like to submit PDFs with their organizational letterhead across the top. And these documents can be anywhere from 2 to 20 plus pages long. Some comments are part of campaigns where multiple commenters may submit a form letter, or they might make minor variations to make it their own and submit that as a response to a Federal Register notice. Agencies who request comments are then tasked with reviewing all of those comments and then responding as appropriate. So there's a manual review process that happens along with all of these notices. Last year, an interagency working group was formed to explore the feasibility of updating how the government captures race and ethnicity information on government forms. And part of that effort was requests for public comment in the Federal Register. And so a Federal Register notice was posted for 90 days. The FR notice asks for comment on issues like combining race and Hispanic ethnicity questions, establishing a Middle Eastern and North African racial category, and some others. Commenters could respond to one of these issues, to some subset of those, or they could have an entirely separate comment. And it was the job of reviewers to summarize those comments for stakeholders, and in some cases to even quantify those comments. I was part of the team that reviewed the public comments for that Federal Register notice. And when I joined the team, they had a spreadsheet with this high-level information you see in the image here about each comment that was output from the regulations.gov admin page. Notably, it doesn't include the text of the comments. The plan was that the reviewers had was to click each of the hyperlinks that you see in column A, go to the regulations.gov website, review the comment, and then come back to the spreadsheet to annotate the information. And this wouldn't have been so bad, except that the notice received over 20,000 comments. So this would have been a painful process to do 20,000 times. So my task was to help streamline this process by collecting the full text comments through the regulations.gov API, put them into a spreadsheet, and then identify exact or near duplicate comments using clustering techniques to aid in the review process. And then finally, to wrap this in some automation so that it was easy to run on a daily basis during that 90-day comment period. The first part of this project involved pulling those comments down from regulations.gov, and I have an extended version of this talk that covers that part if anyone's interested in that. What's important to know for this talk is that I did not deal with the 1,214 comments that had PDF or Word documents as attachments. I only addressed the comments that were submitted as text comments that were entered into the box on regulations.gov. With text clustering, the idea is that for any large grouping of text collected for a specific purpose, there will be some amount of conceptual overlap between comments. And this is easy enough to handle when there are exact duplicates. We can apply labels that say that these are the same thing. It gets more complicated when there are variations that can't all be addressed through some simple text cleaning. There will be minor variations like additional text and synonyms, yet these comments are still have some amount of conceptual overlap with other comments, and we want to capture that. We also don't know how many of these conceptual groupings or clusters there will be before we start reviewing, and that adds complication to it. So by identifying these clusters, we give our manual human reviewers a means for sorting and filtering the responses before they start reviewing them. And so they can group like items together, which limits the amount of context switching they have to do when they're reviewing multiple comments in a row. And these labels can also be used by those coordinating the review process to assign reviewers to particular clusters, for example. So this is the basic clustering workflow that I'll be talking about. You convert your text to some numerical representation, you cluster the comments, and then you reduce the dimensionality down to 2 dimensions so that you can visualize it. And to get the value that I've been talking about, you really only need to do the first 2 steps. Steps 3 and 4 are there to make sense of the clusters that were created. And because visualizations are nice to include in presentations to stakeholders and presentations like this. There are numerous ways to convert your text to a numeric representation. You could simply count the number of words that occur in a particular comment. A more modern way to do this is what Ben was talking about with word embeddings or text embeddings. And these are produced by these large language models, as Ben talked about. And the models get trained on vast amounts of text, and they produce a vector of these floating point numbers for any given chunk of text that you feed into it. And these numbers contain some latent information about the meaning of that text. So the idea is that items with similar semantic meaning should be close to each other in this multi-dimensional space, similar to how we see them together in this 2-dimensional space. And I used the Python sentence transformers package, if anybody's interested in the details of it. And that's a variation of the popular BERT model. So before models were named after animals, they were named after Muppets characters. And so BERT is this variation that I used outputs a 768-dimensional embedding for each comment. Clustering algorithms identify items, and in this case, the items are all comments that are close to each other in this multidimensional space. So I clustered the comments using the full 768 dimensions. There may be some benefits to reducing the dimensionality before you do the clustering, but I thought the clusters that I was getting at were largely coherent, so I left it as is. And you also have a choice, a broad choice of algorithms to use. And there are, a lot of different, thought processes, different options out there. I used both k-means clustering and hierarchical density-based clustering for this project. And so k-means clustering is a good baseline because it's commonly used and it's relatively easy to understand and explain to people if they're curious. The drawback is that you need to specify the number of clusters you want beforehand, and all the comments end up getting put into a cluster, whether that really makes sense to do or not. And with density-based clustering, and for this I use the HDB scan algorithm and the package in Python, the model uses some parameters that you set to determine if a group of points or a group of comments is sufficiently dense to be considered a cluster. And this is nice because the algorithm figures out for you the number of clusters that you have in your data set based on those parameters that you feed into it. And those items that don't make sense as part of a cluster get dumped into a miscellaneous unlabeled group, which if they are truly unique, it makes sense that they don't end up clustered. As I mentioned, it often helps to visualize clusters, so we need to bring down the dimensionality to something that our brain can comprehend. So there are a lot of algorithms for this as well, but for this project, I mainly use the T-distributed stochastic neighbor embedding, very tough sounding, so I use, the acronym is TSNE, which is a little bit nicer. But shortly after I completed this project, I went to a presentation where I learned about the PackMap algorithm, which provides actually much cleaner results for this use case. And that's what I'll show you in the visualization on the next slide. So finally, the visualization step. So you plot your two-dimensional data, and here are the points represented for each point in this plot represents a comment. And it helps to use interactive visualization software so that you can hover over a particular point and read the associated comment. That helps make this all make more sense. I use the Bokeh package in Python for that. Of note here are that the clusters are very tight, and some points with exact duplicates are stacked on top of each other. So this right here might look like a point, but it's actually a bunch of identical comments stacked on top of each other. This can give you a first pass review of whether clusters represent coherent groupings of related comments. And these clusters almost exclusively represent letter writing campaigns with near or exact duplicates. So some of these more diffuse clusters here are ones where there was some near duplicates, and so there's some variation in the text. The visualization also shows, what I'm showing here is the density-based clustering algorithm. So there is this group of unclustered points, and these points are largely unique comments that were not part of a letter writing campaign as part of this Federal Register notice. And if we wanted to, we could dig into this group of comments and identify subclusters, but I did not do that for this work. So the reviewers didn't want to wait until the comments had all come in to start their labeling. They wanted periodic updates of the comments that I was pulling along with their cluster assignments. And there were anywhere from a few dozen to over 1,000 comments coming in every day. So a lot was changing very fast. So to produce daily updates, I built an automated pipeline using Airflow that pulled in new comments and reapplied this embedding and clustering steps, and then uploaded a spreadsheet to an AWS S3 bucket. I shared that spreadsheet and its contents with the reviewers and other stakeholders that were on this project through an rShiny dashboard. And again, I'll remind you that all of these data are public. So the application provided various summaries of the text information, and most importantly, provided a button so that a spreadsheet with the updated comments and cluster information could be downloaded. And this is what the final spreadsheet looked like. So reviewers still had access to the information that they had before, including that hyperlink to view the comments on regulations.gov if they were so inclined. But now they also had the full text of the comment and this clustering information, which allowed them to sort and filter and assign cases amongst reviewers. And this allowed them, so as they were going through, they could apply these, when they were applying the labels, they could see if the next comment in order was a duplicate or a near duplicate. They could, try to make sense of what the differences were between those two comments, and then they could copy previously applied labels if that was appropriate. So as I mentioned, there were over 20,000 comments that came in total. And of that, there were a lot of comments that fell into letter writing campaigns. There were only about 4,300 comments that I would label as sort of truly unique or non-duplicates. There were 82 letter writing campaigns with duplicates, exact or near duplicates, that made up 2/3 of all of the comments, roughly 13,000 comments in total. So understanding these 82 groupings and knowing that one only has to identify the differences, slight variations between them when they're doing the review, really simplified the review process in this particular use case. One interesting, perhaps bit of trivia from this, 14 of the top 15 letter writing campaigns were from members of civic organizations that were interested in seeing a Middle Eastern and North African race or ethnicity category added to government forms and surveys. So going forward, I want to turn this code into packages and so that they're easier to distribute to interested groups. I've been working on extending this work to the PDF and Word document attachments. So it involves, kind of pulling the text out of those and representing those in a meaningful way, even when there's, 20+ pages. It would be helpful to provide more tools for text analysis. Ben covered a lot of great things that you can do with these large language models, but this was just, a small bite-sized piece of that. And it would be helpful to have a user interface as a review tool rather than just using Excel. We use Excel for the full review process. And Excel is wonderful because it's universally available across organizations with varying technical requirements. But it does limit limit you in terms of what information you can pass along to those reviewers. And so thanks everyone, and I look forward to the Q&A.
Thanks, Brandon. That was amazing. Really a game changer when it comes to some of the comments coming in and the volume. Wow, that was fascinating. That's great. All right, Tala, let's jump over to you now.
Great. Can you hear me?
Yes.
And can you see my slides?
We can see your slides, yes.
All right.
Paula, can you also put your video on, please?
Yeah, I tried to click that, but it said that you have to do it. Let me try. Yeah, the host has stopped it. I get a message that the host stopped the video.
Okay, thanks. I'm going to put it on. You can go ahead and start.
And Tala, you might want to switch the settings. We're seeing the presenter like we did before. We're seeing the note slides as well.
All right, 1 second. How about now?
That looks great.
Great. Let me try to start my video again. All right. Thank you very much for the introduction. Thank you for having me here, and great presentations by Ben and Brandon. I just want to, say kudos to Brandon. This is a huge application that I think will introduce a lot of efficiencies for a lot of the work that the different agencies do. We tried this at the FDA, and I'll mention this briefly during my presentation. My name is Tala Fakhouri. I'm Associate Director for Policy Analysis at the FDA. I work on the drug side of the FDA at the Center for Drug Evaluation and Research. Having technical problems right now, but all right. Just the typical disclaimer slide. But before we start, I wanted to acknowledge the executive order that was signed by the President Biden, at the end of October last year, which directed a lot of the agencies within the federal government to start thinking about AI uses generally, about policies and regulations of AI use for specific industries, but also to think about internal deployments of AI to increase operational efficiencies. So I wanted to pause here for a moment to also provide the definition of AI as was described in the executive order. And the reason I'm doing that is because this definition is so wide. It includes perhaps some things that we have been doing for many years, but not specifically calling out as artificial intelligence or machine learning, but it would fit into that category. For us, for our work that we do at the FDA, these definitions are important because it sets the stage for communications that we have with regulated industries, whether it is pharmaceutical companies or medical device manufacturers, and so on. For today's presentation, I initially wanted to just focus on the internal applications, but I thought it would also be great to highlight some external to the agency uses of AI that are very interesting. They are text-based. That's what I'm going to focus on. But it just shows you the breadth of applications of AI for the development of medical products. So first, I'm going to start with submissions that come into the agency where AI, specifically large language models, may have been used. And then I'll talk about some internal applications of language models to increase our operational efficiencies. So I want to first start with a couple of slides to give context. The FDA has been exposed to AI uses for many, many years. This slide is from our colleagues at the devices side, and it just shows the number of AI-enabled medical devices, including those that may use generative AI or large language models, that have been authorized by the FDA from 1995 until today. And you could see this exponential increase. In fact, CDRH has authorized over 700 AI-enabled devices. Most of these authorizations happen over the past few years. On the drug side, we've also seen something very similar. We actually published a landscape analysis last year documenting the agency's experience with, again, submissions. So these are submissions that come in for a drug approval or a biologics approval that would contain an AI or an ML component. And the part of the table on the top is related to the submission type. We don't need to focus on that, but on the bottom, it shows the number of submissions from 2016 until 2021 by the stage in which AI was used. So discovery, usually this is, you may have heard about AlphaFold. These are type of predictions that you can use to figure out how a protein folds, which is very important. It's the first step kind of to identify therapeutic targets for drugs. But the most common use in drug development stage is in clinical research. And I'll give one example that uses a language model for that, which is a very commonly used application of the technology. So normally, the traditional way of approving a drug application would be the sponsor of a drug application would conduct a randomized clinical trial. But because there's this huge availability now of large data sets, mostly data that comes from claims type of databases, so you could think about data that comes from CMS, or data that comes from EHRs, electronic health records, or data that might come from registries. So there are certain registries, cancer registries, pregnancy registries, there's COVID registries, where there's a ton of information available that a researcher or a sponsor for a drug can use this information in their submission for an application for drug approval. These data that come from EHRs or claims or registries, we call them real world data. They tend to be low quality data. They're massive, but they also have problems with missingness of information. There's also the nature of the data is unstructured. There may be combination of imaging with lab results in addition to the clinician's notes and so on. So it's messy. What we see now happening, which is pretty exciting, is the use of different types of algorithms. And here it's a deep learning model, but now also generative AI is being used for the same type of problem, is to take the doctor's notes and transform it into actual variables that you could use in a data set to do a proper analysis to figure out if a specific drug has worked in the real world setting or not. One example that you could think about is the COVID boosters, where a lot of the data submitted actually came from real world setting. And you can again imagine clinicians taking their notes, putting them in the EHR, very messy data, that then you would try to make sense of it and structure it. And you could use language models for these types of problems. So this is one practical example of what we see. Of course, this would introduce massive efficiencies, because normally doing this by hand or manually is both time consuming and resource intensive. Now we're going to switch to internal uses of AI, specifically language models internally. The one example that I want to focus on, or the one use case, is actually by one of the sub offices in the office that I work in, and that's the Office of Prescription Drug Promotion. OPDP is an office that is tasked with making sure that prescription drug promotions are truthful, balanced, and accurately communicated. So this is when you're listening to advertisements for a drug, or if you get a pamphlet from your physician, this office is tasked with making sure that that information that is presented to the consumer is truthful. Normally, OPDP will review, over 150,000 unique promotional materials. So you can imagine how labor-intensive this type of work is. They literally have to do it manually. They have to watch videos. They have to listen to the audios, and then compare that information in the promotional material to what is on the label of the drug, which is regulated by the FDA. They would also have to have access to reviewer notes and internal FDA documentation to make sure that whatever is mentioned in the advertisement is consistent with how the drug was approved and what's on the label. These types of advertisement submissions have increased dramatically. They keep going up, but also we're starting to see an increase in digital advertisements, whether on social media or just online. You'll start seeing some advertisements popping up. That's a very labor intensive, as you can imagine, problem. And this is where we found some really good solutions using AI. So here's just one example that I wanted to share with you. This was an advertisement for a drug. It was actually a video advertisement. And what the platform, the specific tool that we used, what it does is it will take the video advertisement, it will separate it into video, audio, and any actual text that may appear on the screen. It will take that information and it will compare it to what's on the label for a drug. There's always a human in the loop. Our reviewers are always involved in that they would have to check and make sure that any identified discrepancies or issues are manually reviewed. But you can see from the example here, that picture on the right, the VO is voiceover. So it tells you that that specific drug helps preserve quality of life. This is actually for a metastatic breast cancer drug. So that's the voiceover. It's consistent with the image. The graphic says the same thing. And then the text on the fine text says overall survival was a secondary endpoint of the trial, and it explains basically, gives more context. However, this information was not completely consistent with what's on the actual label, so it flagged it. This information was used in addition to other pieces of information to write up what we call an untitled letter that went to the specific sponsor of this drug, basically letting them know that the information provided was not accurate. This is one efficiency that we've been able to introduce using an AI-enabled tool that has, I can't emphasize how helpful it has been, how much time it has freed up for our staff to be able to do many other important activities for their office, but also be able to accomplish these type of complicated tasks so efficiently. The other couple of examples that I wanted to provide, and it's worth thinking about this now with the executive order and this need to have these internal capabilities of AI built up. A lot of our agencies now have probably digitized, I hope. A lot of us have digitized a lot of the information that we house within our agencies. So we did that same thing at CEDAR on the drug side. We've been able to transform any PDFs, paper records, anything that you could think of is now sitting on a platform that we call CEDAR One. So it include information from industry submissions. So these are hundreds of pages that a sponsor for a drug application would give to the agency with all of the data needed for the agency to approve or not approve a specific drug application. It also includes FDA internal data that's generated from the work that we do within the agency. It has FDA published data, and it has external data that we can pull into CEDAR One. All of this information now is sitting on this platform that enables us to do things that we weren't able to do before. One of which, one example that I want to give here is the use of NLPs for deduplication. So we have a database for adverse effects called the FARS database, which has over 25 million reports or records. Some of these reports are duplicate type of reports. We've been able to use NLP to deduplicate this information. This is a great use. It saved a lot of time, a lot of resources. It actually reduces errors too. The other one that's very similar to what Brandon mentioned now is we recently started incorporating LLM within CEDAR One, so large language models, for deduplication, summarization, and sentiment analysis of docket comments. Most of the work that we do, specifically in my office, is we publish guidance documents that are put on the Federal Register for public comment. What we normally do is our staff would pull down all of this information from the Federal Register. They would put it in an Excel sheet. They would separate each comment out into a row. And then they would do that systematically for all of the comments received. Sometimes we have hundreds of comments. Sometimes we have 75,000 comments. So there's a range. It takes a lot of time. It's very cumbersome. A lot of staff hours are basically dedicated to this task. We're now playing with different large language models. Some were trained internally on FDA data, and some we just pulled some available LLMs from the market, and we're basically comparing to see what works best. And right away, what we've noticed from just the very basic task of going on the web, pulling things down, separating them into an Excel sheet, we've already had a 4,000% gain in efficiency. Something that would normally take 3 FTEs for a couple of weeks can now take less than an hour to be accomplished using this type of a large language model. So this is, again, a great example, I think, of a way that this technology can be used for internal efficiencies. I wanted to touch on this because I know some of us are also thinking about ways to deploy these algorithms in ways that maybe not just operational, but that might have some impacts, basically, because of the risk that's associated with deploying the model. Do I trust that model? Do I trust a work product from an AI model? How do I communicate this issue with trust with interested parties or stakeholders? We recognize, especially for the external uses, so the submissions that come in, that these data are just as good, or the information, the models are just as good as the data used to train these models. There are known issues with the scarcity of high quality, large scale, fit for purpose type of data sets, especially in the work that I do in the healthcare side. The data is not that great. So the models developed on these data may not perform very well. The other issue that is challenging, depending on the specific context of use, is the opacity of these algorithms. So we call them black box algorithms. Sometimes it's okay for an algorithm to be a black box algorithm as long as the performance is high. At other times, you may need to understand how the model came up with the conclusions that it came up with. It's important to understand this process because this is how we can assess the quality of these specific models. So it's important to keep that context of use in mind. How are you intending to use this technology? And of course, transparency, very important for us also within the federal government when we're using this technology to be transparent to users on how it's being deployed. And of course, there are issues with oversight and governance. A lot of the publicly available large language models, obviously they're learning, they're adapting, and so the performance might change, which means the quality of the information that you're getting might also change. And there's data privacy, security, and of course, ethical use type of issues. I wanted, though, to end with at least just a general framework that I really like. I keep that in the back of my mind. This is commonly used in something that we call model-informed drug development. It's a matrix that allows you to assess the risk of a specific model for a specific context of use. On the horizontal axis is model influence, and what that means is how much am I relying on information from that model to make a decision? And then the vertical axis is the decision consequence. What happens if my model is wrong? If my model is the medical device, for example, and the decision consequence may be death, and I'm a regulator, I'm relying on this model, so my reliance on it is high, then that model risk may be high. And therefore, the verification and validation activities I have in place are going to be tuned to the level of risk for that specific model. Something to keep in mind as we continue using this technology, whether it's for internal purposes within our agencies or for products that we release to the public. For us at the FDA, what's next is we are currently working on implementing the mandates that are specific to drugs and devices as part of the executive order. We're developing guidance and policy in this area. We actually just announced on our guidance agenda for this year, we're going to be publishing considerations for the use of AI for drug development guidance. That will provide a risk-based framework on how the agency will view the use of this technology in drug development. We will continue to have public education engagement, and I love that I had this opportunity with you all, learning from you as well. And we're going to continue exploring different ways to deploy AI within the FDA. Thank you, and that's all I have.
Thanks, Tala. Those were some amazing use cases. Wow, what a great wide variety of uses there. So for now, we're going to go to our Q&A. Unfortunately, Ken had some technical difficulties. We were unable to get him into the webinar this afternoon, but we'll try to get him back for a future webinar. So Brandon, Tala, Ben, I invite you all to come back on screen, and we can jump into some Q&A here. First of all, thank you for 3 amazing presentations. Those were just outstanding, really very thought-provoking in so many different ways that we can really get so much out of the text analytics through machine learning and AI. So let's jump into a few general questions. And then we can get into more of the specific technical ones as we go along. And everybody with us today, use that Q&A. We've answered some. We'll probably go through those as well, but keep putting them in there, and we'll get your questions into the flow here. So one of the things, as I listened to you, all 3 of you, the different types of use cases you all presented already. Some are obvious, some weren't. What are some other examples of text data or use cases that often overlooked when thinking about opportunities that really could benefit us as government agencies that are just sitting out there? Maybe kind of a related thing is we have a lot of bodies of work. We have a lot of corpora. What's not being used by us? What should we, all of us on the webinar today, what could we be thinking about as far as this? Tala, we'll start with you and then go over to Ben.
So we haven't done that internally, but I know that this is something that's being done by the industry, which is the writing of the first draft of a report. So you could think about, these reports. I know that when I worked at NCHS, reports that you have to publish every few years, where a lot of the language is kind of consistent. You just have to make a few updates. This is where using something like a large language model would be very helpful. It's a low-hanging fruit, in my opinion. Obviously, you have to have checks in place to make sure that someone is reviewing these documents, and that's why I'm calling it a first draft.
Yeah, that's good. I love the first draft, and really captures it well, and it's that good balance. Kind of going back to some of those decision points you had mentioned at the end of your presentation, Tala. Ben, over to you.
Yeah, thank you. That's a really good example of, especially I've found that definitely in times of like trying to figure out your language in different ways and being like just that writer's block, which can be such a pain point often. The area I was actually thinking though more was we have so many different public documents we've published in different ways. For example, your technical reports, these 100-page documents that you can have all this information just available, and it's hard to find or hard to parse for people if you don't know exists. And so using a large language model in some way to create a tool that people can interact with these documents in a more user-friendly way or a faster way. If it saves you that, 20 minutes of time just trying to scan through a document to find that piece of information you need, that's a real productivity gain. And there's a lot of exciting work in the field about how can we best use these large language models with retrieval augmented generation to help with this task. So, over.
And yeah, that was the use case. The retrieval augmented generation is something I'm very excited about, and something that I've thought about in the context of this the Federal Register comment thing as well. Like recently, when I mentioned that I was starting to look into the pulling of the PDF documents, the thing that eventually got me looking at that was the OMB request for information related to the a memo that goes along with the AI executive order. They received like 200 comments from like all these big tech companies, from civic organizations and things like that, 20-page documents. And so I was like, oh, wouldn't it be great to sort of digest all that great information from all these companies about how they're thinking about the regulations that the executive order puts forth and that the OMB is trying to put together that memo for. And so that's going to be my use case for learning retrieval augmented generation.
That's great. So Brandon, you had talked about some traditional techniques and then some new techniques with natural language processing. What do we all think about? What other new techniques really hold promise for our missions as federal agencies? Chain of thought prompting, mixture of experts. What comes to the top of mind for the three of you?
Yeah, certainly summarization. I think we get so much stuff that being able to summarize it in a trusted, make sure that you're getting all the right information out of the summary that you would have gotten out of the full document would be a good use case. And then another thing where we're sort of experimenting with it is with what they call question and answer systems, very similar to what Ben was talking about with the retrieval augmented generation, where you can query a document and say, and try to extract very specific information from it. So, for example, if you're looking for one of the things we're experimenting with at BLS is if we get a bunch of news articles related to workplace fatalities, right, that might show up in news articles, and we have certain data points that we're looking for, sort of like, I guess, morbidly sort of think about summarizing it as data points, but just for the sake of this, go with me. But we're looking for particular things, right? Like how was the person, injured? What was the date? These sorts of things, and you can use these large language models to query the news article to extract that information that you might need for your data collection. So it'd be a good way to make use of data that we're not currently able to make use of at scale.
Yes, Ben.
Yeah, I was gonna jump in. That was a great answer, Brandon. I was actually gonna talk about one of the other things that you mentioned, Ed, which was chain of thought prompting. For those of you who don't know, this was one of the terms that Ed mentioned. It's kind of like in my presentation, I mentioned few shot prompting, where you give actual examples. Chain of thought kind of takes it a step further, where you add in actually reasons why that example falls under the different case. So for example, if you're classifying a piece of text, if this is very qualitative for all you qualitative people out there, and you're giving it for your coding, for your open-ended survey responses, you can actually give the large language model some reasons. Okay, this is the category that this piece of text falls into. Here's why, and actually explain it to your model. This is why it matters in so many different ways, which is just so fascinating. It's not going to be applicable in every single case or instance, but for those of you who do qualitative work in that way, being able to explain the why to your model is a really fascinating use case moving forward. Over.
Right.
And certainly too, we don't have a lot of experience yet with the very large language models, your GPT-4s and whatnot, but I think that sort of being able to use the sort of compressed knowledge aspect of it, which is where a lot of people get scared about the hallucinations and these sorts of things. But one thing that I did experiment with is I was interested in learning about a broad range of software. So I looked at those market scan diagrams, where they say like, this is all the software used for machine learning, or this is all of the software used for DevOps, copied that into a spreadsheet. And then I asked GPT-4, look up each one of these, tell me what it does, tell me, how it would be related to this particular topic. And I got back some reasonable responses. I can't say for sure that they're all 100% accurate, but 270 products comes back in just a couple of minutes. That's definitely, some refinement and time savings to the extent you can kind of get to the point where you can trust it.
I wanted to, something you said there, Brandon, and I want to go to one of the questions that came in the chat here in the Q&A. It was for a small government agency with little background in Python and R, what's a good step-by-step document or site to get started in doing some text analysis? and this was specifically for comments and citizen surveys. But I think going beyond that, for folks who are getting into this, where's a good place to start? Yeah, Ben.
I love this question so much because it's so exciting. There's such a wealth of knowledge out there in so many different ways. It's really hard getting started. That initial step, it's really hard to put your toe in. So I'm just going to encourage all of you to, if you want to, just try. It's okay to fail in all these different cases. But one of the most fascinating and exciting parts about large language models as a whole. Actually, when ChatGPT came out, I was actually in the process of getting a second master's degree because I wanted to increase my skills. And following that traditional route, you would use a second master's degree to kind of gain those skills. But I actually tried using ChatGPT for the first time on a coding task, and I realized it met all of my goals in terms of improving my performance in these different ways. And I dropped out of my master's degree because using ChatGPT met all of my goals. Of course, I already had this position. I didn't need it for a title, anything like that. But these generative AI tools are your friend in these cases. Of course, it could be wrong. Of course, it could be all those different things. But having essentially a personalized one-on-one instructor you can ask questions to is so helpful. Like I have a supervisor data scientist who I can ask questions to at my place of work, but I can't ask him questions 24/7. He has a day job. So I can ask ChatGPT though all the time, as long as it's outside of actual work, following different work practices, of course, all of that. But in general, you can ask those different types of questions. So there's a lot of also other guides out there in those many different ways. And just even as a starting point of, I want to do this task, what's the field going in? Or can you describe overall how this is done in so many different ways? Generative AI just as a whole offers so much capabilities here, and it's just so exciting. So I encourage all of you just to try it. It's okay to fail, and the tools there are really your best friend. So over.
I just want to acknowledge that this is a very difficult question, right? The field is growing so rapidly, and we need to keep up. So how do we gain the skills needed to be able to utilize these tools? This is something that I don't know that we can resolve this here, but I hope that it can be answered through some of the mandates that we have to deliver as part of the executive order, which all agencies should be kind of responding to. A lot of it is upskilling, right? It's just training staff to be able to do this type of work through formal mechanisms.
And I would just add that the best way to learn is to just jump in and start doing something, because then you do the grinding that it takes to do the Google searches, watch the YouTube videos, find all the right resources. And when you have something, and I personally, I like to start with a personal interest use case and not necessarily something connected to work. So when I first got into text analysis, I was looking at State of the Union addresses, things like that, it's just sort of a personal interest. And then that helps you get over that initial hump of I'm frustrated, but I can meet I can get to some place that's personally interesting to me, and that usually helps get you past that initial frustration point.
Tala, something you said, I was really impressed with where you've gone and where FDA has been able to go, doing something at scale. Myself, my team, we've been able to do a bunch of proof of concepts, but to be able to be in production and at scale is really that huge thing. So kind of going from that last question of how do I get started, I guess for us, especially in a federal agency, we have additional contours and guidelines on the IT side, on the policy side that we need to overcome. So what's been the biggest implementation challenge after developing a proof of concept or a model in the system, and really for all three of you?
Yeah, and we've had conversations, FDA, with our colleagues at CDC, with NIH, for implementing some of these platforms, specifically that one that analyzes advertisements and then compares it to the label, because that means that this platform has to sit on FSMA high compliant, it has to be within FDA systems to be able to do this work and not be connected to the internet. That is the biggest hurdle, I think, from an implementation point of view. But what we've been seeing now, after we've been able to implement these types of platforms internally, is once you've kind of digitized everything and you could buy the LLM from an external source, whether it's MedPalm, the Google LLM that's trained on medical terminology, or one of the many other large language models out there, you could prevent it from being able to learn or share anything from the internet. So that is the other big thing for us, is once we digitize the information, now there's a lot of information these models can be fine-tuned and learned from as well. Other than that, you're relying on the quality of the internet, which is not that high.
So yeah, I would say sort of like an interesting tidbit to my presentation is that I actually wouldn't be able to do it on my work computer at this point. This is, as of July, we'd sort of implemented an AI policy that would block me from getting access to the large language models that I use to do the embeddings, right? So that cybersecurity aspect is a big part of this that we're kind of now working through the steps to figure out. And I think, yeah, to Tala's point, like once you kind of figure out what the agency needs are, then there's certainly ways out there. Like, AWS has Bedrock, and Google has Vertex and Gemini, and these things kind of built. Azure has some GPT features built into their like federal services, so you can kind of get them into your sort of extended network. Again, but that's all like theoretical at this point for us. We haven't quite gotten there yet, but it seems like a solvable problem. But that comes with building the sort of expertise on that side of things, like building the comfort level with those people that have to take on that responsibility. When you say like, oh, by the way, you're going to get, take the blame if data gets exfiltrated, right? Like it's you have to kind of build that level of confidence amongst those people that, and then of course, you have to run it through all of the bureaucratic things to sort of get to that point. But I think it's a solvable problem. And then the other thing outside of those like truly massive models that need to be hosted in the cloud is all of those models that Ben was talking about that are like, you could theoretically locally run them. They require large servers and stuff within your network. But that's the other place where we might find some middle ground with the cybersecurity folks is, scanning some models, getting them onto local hardware, and showing that they don't have any sort of external dependencies that they're reaching out to, and running them there.
Yeah, I can kind of follow up there with Brandon's, especially talking about that local models. Not to make you too jealous, Brandon, but SANS actually I trained on the laptop I'm presenting from. So not to make you too jealous there. But that is a major point in so many, it really depends on the scale of the task at your hand. So for example, for SANS, the large language model we've trained at NCHS and have published, that's available model card at cdc.gov. There's so many different parts. You have to have your subject matter experts who really understand the data, working really closely with the team who are actually implementing it in so many different ways. And especially when you're using these large language models, observing the quality of the output in so many different ways, that is a very time-intensive process. And for us to be able to release that model, we have to be very comfortable and very confident in it. And that only happened after literally a year of different surveys going through and seeing the different output in those different ways. And so be able to spend that time and having that commitment from everyone to be able to put time in is a big thing. I do want to say that for different FedRAMP authorizations, there are some cloud providers out there. For all of you who use Azure, for all the federal agencies, OpenAI does have I should say Microsoft has a FedRAMP authorized instance of ChatGPT through Azure. And so that is available depending on your agency. There's so many different factors out there. Some are looking into it, some are not. It really depends. There's a cost aspect, all those other different factors. But yeah, it really depends at that point. I mean, getting a secure computing environment at the scale of running these different large language models is still a challenge. Even like for SANS, it's 500 megabytes in size, so you can run it on a local laptop. But for something even like Llama 7B, that's 16 gigabytes in size, running that on, now you need a GPU to run it on, having that GPU server in place. That is, like Brandon mentioned, that's a big structural challenge in many different ways, especially if it's something new to your agency of how can we gain access in these different ways. So oftentimes that's through just cloud providers in those different ways, but then getting in and getting access together, it's a challenge as a whole, and it requires a lot of coordination. CDC has some exciting things in this front, but I can't say much more.
Oh, you're muted.
I am muted. Oops. All right. So a lot of interest in the responding to comments submitted to dockets. That's a big theme throughout the questions here. So a couple questions back to you. What metrics or criteria should we be thinking about to evaluate the effectiveness of a clustering approach when we're trying to streamline a manual review process there? And maybe a related one is how easy you think the code you developed can be adopted for other agencies on the webinar today?
Mm-hmm. Yeah, it's a good question because my title sort of implied the efficiency, but I didn't actually measure it. I felt pretty confident that there had to at least be some amount of efficiency in it, but it did not measure it as Tala did. And she like, I'll go with the 4,000% increase number. But no, I think one of the issues that we had and one of the things that I hope to solve with a potential like user interface is actually having the ability to measure the per item reviewed timing, which you can't do in an Excel spreadsheet. But yeah, there's the main measure that I used in terms of feeling like I accomplished something was the feedback that I received from the manual reviewers and from the stakeholders that sort of were the downstream consumers of their information, which was, they were very appreciative of it, and it's sort of like I had this feeling of having turned lead into gold almost. Like it felt rewarding in that sense. So, but yeah, I think certainly the time it takes for each particular comments, and aggregating up to a larger thing. And then also I think there's something about the to the extent you can measure the accuracy and the intercoder reliability when those things are being used. One thing that we deal with some of our automated coding systems for other things is people becoming too reliant on it. So if my thing said, oh, this is clustered, so it's probably somewhat of a duplicate. If somebody just copied, pasted their responses and missed out on something important, that would be potentially problematic. And so in a sort of a large operational use case, I would want to do some user testing to make sure that that wasn't the case. In terms of sharing the code, that's certainly my intention. This sort of got backburnered because like so many other things come up, but that's certainly my intention. I have the sort of raw code now, but I'm, everybody's like a little bit embarrassed to share their code of, what might people find, but I don't know at what points it'll break down, but for people that are comfortable with adapting the code to their use cases, it's probably reasonably ready now, but I kind of wanted to turn it into something that's more generalized and more packaged so that people can just install and use without too much problem.
Tala.
Well, I was just gonna say, Brandon, someone just called you in the chat AI chemist. Which I just want to ditto that. Like, it's such an awesome application that saves people so much time. I feel like all of us should be doing this all the time. One thing I wanted to mention, Brandon, just based on our internal experience, we tried to use the same algorithm on a few different guidance documents, and it performed pretty well on all of, even though they're different type of documents. So it was applicable to a different context. When we explored using LLM for that type of work, it was very dependent on the prompts, the quality of the prompts that you gave. So that's something to keep in mind, which actually makes it very difficult if you're using like a chat GPT like thing to analyze comments. Consistently getting the same response may differ depending on how you're asking the question.
Tala, I saw you'd answered one of the questions in the chat, but I was super interested in examples of AI devices, and you've put a nice list in there. But could you talk for a second about AI devices?
Sure. So the link that I put is for every single authorized device. If you go to that page, you can actually go to this specific device and learn more about it. There are so many different types of applications. Some of the most common ones, at least the females in this audience may be familiar with it. If you get a mammogram, you'll be asked, there's an AI algorithm that will be reading the images and provide that information to the radiologist, kind of augmenting. It's a clinical decision support tool. So that AI tool reads the images and comes up with its own conclusion about what it's seeing in the radiographs, and then provides that information to the clinician. Another AI use that is pretty awesome. This is that we recently, actually, the CEDAR side qualified it as a drug development tool type of, a tool that you would use in a drug development program. It's basically multiple things. So when we say AI model, I'm not talking about one algorithm. It's so many different models contributing, right? Or so many different algorithms contributing. So that was a tool that is used to measure depression. And it relies on things like the words that you're saying as you're interviewing a psychiatrist, perhaps, but also your facial expressions. If you just look sad, it will be able to detect that. Detects changes in your voice, your movement in the room, and your eyes, how they track. So this is one use case of how the technology is being applied. Another one, and this is not an AI-enabled authorized device, but just to give you a flavor of what's out there. Normally, when a submission comes to the agency for approval for a certain disease, let's say lung cancer, you have to do a 6-minute walk. This is how we would measure an outcome. Can you walk for 6 minutes? How many steps can you walk in 6 minutes? These types of assessments were done manually, quantitatively, but with a lot of qualitative differences. And now you could just put a sensor in a person's home that monitors their movement throughout the day. So it actually increases the accuracy and the precision of estimates because you have a ton of data on individuals. More data might in the future translate to smaller clinical trials. Smaller clinical trials might in the future translate into drugs being approved faster, right? You don't have to recruit and retain patients for many years to be able to collect information if you can have that type of extensive information collected on them passively. So these are just a couple of examples.
Thank you, Tala. That was great. Great. I want to turn to life in a federal statistical agency, and a lot of the data collections we do, we have open-ended survey responses. Talk to us a little bit about, as we're using it, thinking about using it to help with that part. Somewhat similar to comments from a Federal Register, but somewhat different. And maybe my thinking is, what if we're seeing things that the model hasn't anticipated, either new types of responses, new things that how do we deal with that?
Yeah, I'm happy to talk about that a little bit. It's a really good question, Ed. I say that as somebody who I've spent a lot of time in this field. It really depends kind of what context you want the open-ended survey response to use. I mean, the traditional how you handle open-ended survey responses is use it either when there's too many categories to really put into a closed-ended question, or you don't know enough yet to have a good sense of those different categories that you put in. So oftentimes that's really the whole point of an open-ended, to say, hey, we actually don't know. For example, at NCHS, when COVID came out, we had this whole question of, okay, telehealth is a thing now for people going to the doctors remotely. We have no idea how to test this because all of a sudden it got adopted. So let's just open-ended prompts. This is our best guess. We'll find out information, and this will help with future questions. And one of the things that actually has been mentioned in the questions is kind of this field called topic modeling, which is kind of as an exploratory step to see really what's in your data. It's really important to be able to see and look at what's going on there, especially as you're keeping that human in the loop. And so one of our most fascinating use cases we've done at NCHS is provided large language model based topic modeling to see kind of what's out there. One of my favorite cases was actually in response to the question of how has COVID-19 impacted your life. We would not have noticed this, but for some people, it was actually casinos being closed was the biggest impact because some people just love to go to casinos. And I wouldn't have noticed that in like a manual human review part, but being able to give that to your subject matter experts and then being able to say, okay, here's 20 topics. Let me look over and see how do these match up with how we expect them to. That's a beautiful way of large language models holding, and you're not restricting into these are the set categories in the different ways. You're keeping that human overall responsible for the different areas. But yeah.
Great. Well, Tala and Brandon want to give you a chance to weigh in on this one before we close out for the afternoon.
Just very quickly, I know we didn't talk about that, but I think there are a lot of applications that could be very beneficial to federal statistics where we're thinking about ways administrative data can augment the data that you get from a survey. So I had mentioned this EHR phenotyping, right, that we see in the real world setting. You could imagine doing similar type of phenotyping using passively collected information on individuals that you would normally survey. This can potentially be used to augment data that you collect through surveys. Just gonna throw it out there as a potential interesting use case.
That's great, Tala.
Yeah, and I'll just mention quickly that you'd talked about the robustness of this process to a bunch of different types of use cases and a bunch of different types of texts coming in. And that's one great thing about these large language models is that they're trained on a lot of text. So the hope is that they've covered a lot of different things, including misspellings and some other things that might make their way in there. When I first started trying to do this work, it was with just, counting the frequencies of words in all of the different, statements, not necessarily for the Federal Register comments, but for like website comments and things. And once you get all of the misspellings and all of the various things, you just have the vocabulary that's huge and very, very sparse, a lot of zeros in there. And it makes it very difficult to work with that data. But the large language models sort of help a bit with that. And then you can always, do your best to, fine tune those models, as Ben was talking about earlier, to sort of fit to your use case. If there's a lot of, like the Middle Eastern and North African racial category is called MENA. So there's just a lot of people that said, like, I support MENA. That, it's hard to say whether the large language models would pick that up, but if you kind of train it to recognize those sorts of things, it might start picking those up.
Great. All right. Well, I can't believe this 90 minutes is gone, but we are at the bottom of the hour, so I'm going to close this installment of our webinar series. A huge, huge thank you to our speakers, Tala, Brandon, and Ben. You've been so generous with your time and your thoughts, so much energy, and a lot of great discussion in the chat as well as live here, so thank you. I also want to do a big thank you to our sponsors at the American Statistical Association, NORC, at the University of Chicago, and RTI International. And of course, a big thank you to everybody who's dialed in today. We really hope you're going to join us again in a few weeks for our next installment on AI in federal government. We're going to cover image analysis, methods, and use cases. It'll be a great one again. You can find more information about upcoming webinars, how to register, at the NISS website, niss.org. If you're interested in watching this again, if you go to the NISS YouTube channel, you can see this and also the presentations. Thank you and have a good afternoon.